Okay, over here in question number 112, arrange the following alkyl benzenes in the decreasing order of percentage of orthopara ratio of the products formed in nitration. So over here we have to first draw all the structures. So toluene is basically like this. Okay, toluene is, this is your toluene. So there is this one methyl group over here. Now if you look at cumene, cumene is basically, this is your cumene. So the group size has increased. Okay, now for tertiary butyl benzene, obviously it is, so this is even more bulkier. Okay, and the other one, which is ethyl benzene, we will say something like this. So if you look in terms of bulkiness, then you will see that bulkiness, we will say 3 is more bulkier than 2, which is more bulkier than 4, which is more bulkier than 1. So as this bulkiness increases, substitution at ortho position will be decreasing. So bulkiness increases, EAS at ortho position decreases, whereas for para increases. Okay, that is what we will say. So that way, if we say, then the ortho-para ratio will be highest for toluene, then it will be 4, then it will be 2, and then it will be 3. So that should be our answer for ortho-para ratio of products formed in nitration. So we will say 1, 4, and so answer will be B. Next is, which one of the following substrates does not participate in Friedel-Crafts alkylation of benzene using AlCl3? So it has to be basically, it says does not participate. So for Friedel-Crafts reaction, we know the alkyl halide, this carbon joined to bromine has to be sp3 and not sp2. So let's look for the sp2 carbon joined to Br, and that will be the one that will not be undergoing Friedel-Crafts reaction. So we can see this is sp3, this is also sp3, that is also sp3, this is the one that is sp2. So this is the one that will not undergo Friedel-Crafts reaction, and that should be our answer. Over here, which one of the following statement is not true about the reactivity towards aromatic nucleophilic substitution reaction? So for nucleophilic substitution reaction, obviously 2-chloropyridine will be more nucleophilic or reactive than the chlorobenzene, because if you compare the two molecules, which is obviously, say this is the chloropyridine and that is my chlorobenzene. So this particular carbon we are concerned about. So if we see that over here we have a nitrogen which is pulling the electron density from the carbon, being more electronegative. So this will be obviously more reactive than this one. So this is true. Iodobenzene Ci bonds are weaker than CF bonds. So obviously they are more reactive. 2-chloro-nitrobenzene is more reactive than 3-chloro-nitrobenzene. If you just draw the 2-chloro-nitrobenzene, okay, which is this one, and 3-chloro-nitrobenzene means it is occupying the meta position with respect to nitro. So over here the negative charge after attack by nucleophile, because this bond will break, okay, this pi bond will break. It can be stabilized by the minus M effect, okay, but here only minus I is operating, okay. Over here minus I is operating and also minus M. So this is more reactive obviously. So this is true. That means option D is the correct answer. Okay. Just by elimination we can say that. Next, which one of the following is correct sequence of events for the preparation of ethyl 2,4-dinitrophenyl ether? Okay. So let's do the reaction, okay, and you will understand why and what is happening over here. So the first step, if you do, it will undergo nitration, obviously. So if we think of nitration like that. Now over here, this is a highly deactivated system. So if you are trying to do this Br2 FeBr3 electrophilic substitution reaction, I think this will not be undergoing. Again, let's see, this one will lead to the formation of chlorobenzene, which is a moderately electron rich system. And if you're doing nitration, then obviously it is an orthopara directing group. So every likelihood that the nitro groups will enter. And this, if we think, is being attacked by OET, this is also possible because this will undergo nucleophilic addition substitution reaction. So over here the product will be formed. Okay, so possible. Okay, so this is looks like the possible answer. Let's do the option C. In option C also we have this, but this is not an electron poor system. Okay, for this reaction to be possible with OET, okay, we need some nitro groups in the 2 or 4 position. So this reaction will not take place. Next one, they have given aqueous NOH, and I think there is going to be no reaction over here. Next, 116, the number of 1,2 rearrangements possible occurring in the following transformation. Okay, let's do. So over here, obviously the carbocation will be formed. So we have been given this one. This is the CH3, that is the OH. Then, yeah, 1, 2, 3, 4. So let us take this out. So what will be formed after taking a proton? Or let's say that over here we are using SOCl2. So obviously this will lead to the formation of a carbocation, right? So let's think of formation of a carbocation, and so over here we will draw what? This is the methyl, this is the 1, so this is going here via ring expansion. So each time there will be a ring expansion like that. So if you are having a ring expansion like this, suppose, okay, then the positive charge will come here. So again another ring expansion will happen. So that will be like this again. So another ring expansion similarly one can think of like that. So 1, 2, 3. Another ring expansion one can think of 4. This is the other ring expansion. And now that would mean the positive charge will come here. And there is a H over here. Okay. So this will be going away, giving you the product. So how many ring expansions are possible? We will say 1, 2, 3, 4, 5. So answer would be 5.